Okay, welcome back. Next up, we have Nathaniel Bottman, who is going to tell us about the relative two operad of two isosahedra in symplectic geometry.
Okay, thanks for the introduction and also the invitation. It's a real treat to be talking to a sort of operatic audience. I'm a symplectic geometer and I don't usually get to do that. And I'm going to be telling you about this family of abstract polytopes called two isosahedra that arose from kind of totally symplectic origins, but turns out to be an interesting object that has a sort of operad-like structure. And I'm really curious to hear if people have connections or whatever else that they might think of when I tell you about this. So I'll be all ears to that. Okay. So I'm going to start out by telling you about some symplectic background. And of course, I won't assume that you know anything about symplectic geometry, specifically about the Fukaya category and how it connects with isosahedra. Then after that, I'll tell you about this new object called the symplectic A∞2 category and what that has to do with this relative two operad of two isosahedra. And then if I have time, I'll tell you about some connections with the Fulton-McPherson operad. And then down at the bottom, I have this sneak preview to, I hope, convince you to pay attention through the beginning. And on the left, we have an example of a two isosahedron. And on the right, the sort of combinatorial instantiations of that. So I'm not really going to talk about symplectic geometry today. I'm going to tell you about some combinatorial and operatic things that arise there. But I do want to give you some motivation. So I'll tell you some sort of real fundamentals in symplectic geometry right now. So the first thing is just what is a symplectic manifold? By that, I mean a even dimensional smooth manifold M equipped with a two form, omega, the symplectic form. And I require that to be closed and to be non-degenerate in the sense that its top wedge power is nowhere vanishing. So a couple of quick examples would be when M is any real surface and omega is any area form. Another one that sort of reflects the historical origins of symplectic geometry is when M is the phase space of a Hamiltonian dynamical system. And then there's this class of distinguished submanifolds in symplectic manifolds called Lagrangians. And these are any embedded submanifold of half the ambient dimension with the property that the symplectic form vanishes on them. So one example of that would be any curve inside of a surface. So for instance, here's a symplectic manifold, the sphere. And here's Lagrangian. Okay. And it turns out that Lagrangian submanifolds come up all over the place in symplectic geometry, to the extent that Alan Weinstein said that everything is Lagrangian, meaning that a surprising proportion of symplectic concepts can be formulated as Lagrangian submanifolds. And so now we get to this invariant of a symplectic manifold that's built out of Lagrangians, which is called the Fukaya A∞ category associated to a symplectic manifold. And this came out of the work of a number of people, but chiefly Donaldson, Fleur, and Fukaya in the late 80s and in the 90s. And I'm going to totally ignore the huge issue of exactly what geometric hypotheses you need to put on M so that you can actually construct this thing. So, okay, given an M, giving a symplectic manifold, we want to associate this invariant, the Fukaya A∞ category. And I don't exactly know who's in the audience, so I don't want to insult your intelligence, but I'll tell you in a second what I mean by an A-infinity category if you haven't seen that before. It's something like a category, so the objects are the Lagrangians in M. And instead of having one associative composition operation, we have a whole family of them. For every arity D at least one, we have a composition operation called mu D. And the way it's defined is by equipping M with an almost complex structure J, and considering certain maps, which are J-holomorphic, whose domains are disks with some boundary mark points. And so it doesn't matter too much just what my maps are, but what is going to matter for this talk is the nature of the domain. And so specifically that I have an arbitrary number of boundary mark points, and one of them is distinguished. So we think of that distinguished mark point as the output mark point. And we don't constrain the configuration of these boundary mark points. And what I want to focus on is why the Fukai category defined in this way I've described turns out to be an A-infinity category. The reason for that is that the way we've defined our composition operations is by counting maps whose domains are disks with boundary mark points, one of them distinguished. And let's give that a name. So I'm calling that MD with a bar over it to indicate that we compactify those configuration spaces. And the thing is that these actually give you a topological realization of the associahedra. A category over the operad of associahedra is exactly an A-infinity category, and so that's quote unquote why the Fukai category is an A-infinity category. And to sort of get warmed up here, let me just write out one example of one of these configuration spaces of domains. So this is M4. So we have disks with 5 boundary mark points, one of them distinguished. And we compactify that thing, and I claim that we get a pentagon. And so let's work out some of the edges and vertices of this thing. So the interior parameterizes just, like I said, disks with 5 boundary mark points. And we're compactifying by remembering the fashion in which mark points collide when those collisions take place. So for instance, we've gotten this upper right edge right here in the situation that the upper right 2 mark points have collided. And so there's not much interesting information to remember then, but nonetheless, we record the fact that they collided by bubbling off this circle right here. Similarly, we've gotten this vertex up here when the upper left 2 mark points further collided from that upper right edge. And I'll draw a few more. That's when just the upper left 2 mark points collide. And so forth. I'll do a couple more. Maybe one more. Okay, and something that you might be more familiar with in terms of presentations of the associahedra is to present the associahedra as the post set of stable planted trees with a certain number of leaves. And maybe I'll kind of draw those pictures next to these, so you can see how that correspondence goes.
Nate, there is a question in the chat from Emily.
Yeah.
Can you access the chat, or do you want me to read it?
I can. And is it better for me to read the chat or for me to let Emily say it?
Whatever you prefer. Emily, if you want to just...
So Emily is saying that she thinks of the bubble as having a distinguished mark point, the point where it meets the larger circle. So for instance, for this bubble here, that distinguished mark point would be the point where it meets that larger circle. And she thinks of the point where the bubble touches the circle as a non-distinguished mark point on the larger circle. Absolutely. And so when we make that kind of, when we do that thing that Emily is suggesting, what that would be doing is identifying the different faces or compactified faces of the associahedra as products of lower dimensional associahedra. So for instance, that upper right edge, we'd be seeing as M3 bar times M2 bar, where we're kind of cutting up that degenerated tree of circles into, oopsie, sorry about that. There we go. I guess I need to re-share my screen. Something happened. Okay. So we're sort of cutting up that tree of spheres into these two spheres, or circles, I mean, not spheres. Like so. Where this larger circle here gets identified with this one, and similarly for the bubble. Yes, that's right. This is indicating the composition operation on the operative associahedra. Yes, and I will come back to this point a bit later. Thank you, Emily. And so what I want to kind of emphasize here is that there's this principle when you're defining algebraic gadgets in symplectic geometry in the usual way, where you count rigid pseudo-holomorphic objects of one form or another, that the algebraic nature of that object, so for instance, in this case, the fact that the Fukaya category is an A-infinity category, is inherited from the nature of the domain moduli spaces, and particularly their operatic structure. And we'll see that again in section 2 when we talk about this more complicated gadget, the symplectic A-infinity 2 category. So let me just pause there before we get into that next section and see if there are any more questions. Okay, great. Okay, so we're gonna keep talking about the Fukaya category. And I should have said that this is a very important operation, invariant in modern symplectic geometry. And what I want to talk about now is the fact that in terms of the definition of the Fukaya category, there's not a self-evident notion of functoriality baked into it. It's not even clear a priori with respect to what sort of maps we would ask for functoriality. And that is kind of a hindrance to efficient computation. And so Verheim and Woodward, in a series of papers posted around 2010, addressed this. And what they said is that the right sort of map between two symplectic manifolds that should induce a functor between their Fukaya categories is Lagrangian in their product. So when we think of a map from M0 to M1, we're going to mean a Lagrangian L01 in their product, or a Lagrangian correspondence. We put this minus here because we flipped the sign of the symplectic form on the first symplectic manifold, which sort of leads to a reasonable theory. So for instance, once we've done that, the diagonal in M minus times M becomes Lagrangian. And so what they said is that that should induce a functor FL01 between the Fukaya categories. On the level of objects, it's quite straightforward. if we take an object in Fuch of M0, so a Lagrangian L0, we think of that as a correspondence from the point to M0 and just compose it with L01 as correspondences. And so explicitly that means we take the fiber product of L0 with L01 over M0 and then just project it down to M1. And a theorem of Gilliman and Sternberg from the early 90s says that that's generically an immersed Lagrangian. But where this gets more interesting is what we're doing on the level of morphisms. And so similarly to how we define the compositions in the Fukaya category, we're going to count some pseudo-holomorphic maps, but somewhat different ones. We're going to count so-called quilted disks. And I won't tell you what that means in terms of the maps, but in terms of the domain, we're taking a disk, we're putting boundary mark points on it, one of them distinguished, and then we're drawing this circle, which is tangent to the boundary at that distinguished mark point. We're putting an interior circle into this disk. And that's the domain for the kind of maps we count to define this functor on the morphism level. And we again see this sort of operatic principle that the nature of the algebraic thing we're building comes from the operatic structure of the domain moduli spaces. In this case, we're looking at moduli of disks with this one interior circle tangent to the boundary at one point with some number of mark points on the boundary. You may or may not recognize this as a geometric realization of the multiplahedra. Which is a module over the associahedra studied by Stefan Forsey and others, which parametrizes, or I should say maybe encodes, the algebra of being an A-infinity morphism. And so of course it makes sense that that would come up here where we're trying to define an A-infinity functor. Sorry. They went a little bit further than this. It's not true even that the functor associated to the composition of two correspondences is the composition of the functors, but they established a homotopy between those two different functors. They did that via these quilted disks with 3 patches, but they stopped there. They didn't build higher coherences, and something that's maybe more foreboding is that when they studied these quilted disks with 3 patches, they ran into this strange new kind of singularity formation, which is depicted kind of impressionistically here. So this is sort of a mashup of what's happening in the domain and the map. Specifically in the domain, these 2 interior circles are colliding. And in the map, the gradient is blowing up at a point on this yellow bit. And so the point is that in the limit of such a degeneration, you can get this sphere with 3 patches, which they called a figure-8 bubble, because if you look at it from the South Pole, those 2 circles look like a figure-8. And so what I've been working on this proposal over the last 5 years now for a way to complete their picture to something that's a self-contained way of describing the functoriality of the Fukaya category, specifically a way of including this figure-8 bubble and moreover building a whole hierarchy of higher coherences, which they started with their collection of homotopies here. And so what I have proposed is that the way to do this is to build something like a 2 category, but not quite. It's the symplectic A-infinity 2 category, or SIMP for short. Now, okay, so ordinarily what's a 2 category? It's something where you have objects, and Hom from one object to another is a category, a one category. In this case, it's something like a two category. The objects are symplectic manifolds. And now Hom from one object to another is going to be the Fukaya category of the product, which is in particular an A infinity category. And what I'm going to be telling you about is what an A infinity two category is. And that's something that comes out of how we define compositions on the level of two morphisms. So what we do to define composition of two morphisms is by counting quilted spheres. Some pseudo-holomorphic maps whose domains are spheres like this one, where you have as many circles as you like, which all intersect tangentially at the South Pole. We think of the South Pole as the output mark point, and we can have as many input mark points as we like on the circles. And so these maps are called witch balls. As in the two previous instances of when we saw some pseudo-holomorphic maps appearing, the algebraic nature of SIMP is going to come out of the structure of the configuration spaces of domains. And so that's what we're going to talk about for the rest of the talk. So let's give these things a name. We're going to call them 2m sub n bar, these domain moduli spaces. And what n is that tells you that's a string of non-negative integers. The length of that string, called r, is the number of circles. And the entries are just how many mark points appear on the various circles. So for instance, if you had 2, 0, 0, that would mean you have 3 circles with 2 mark points on the first and none on the other 2. And let me write down 2 presentations of this thing. So the first is just what we've seen already. These spheres with R circles on them, intersecting tangentially at the South Pole. And on the ith circle, you have n sub I blue points. So for instance, on the first circle, we have n sub 1, and so forth. We identify 2 configurations if they differ by a Mobius transformation. So that's what the squiggle means there. And then we compactify the space in a way that I'll get into in the next slide or 2. And another way of presenting these is we can think of the sphere as R2 union infinity with the output, the red point at infinity. And then this picture becomes a copy of R2 where the lines, those circles, are now vertical lines. And now the Mobius transformations that keep the lines vertical and keep infinity infinity, those just become translations and positive dilations of all of the data simultaneously. And so depending on which manipulation we're doing, one or the other presentation will be more useful. Okay. Oh, and I should say before I move on that these spaces are what are called 2 associahedra. And so we'll work out an example in a second. But before I do that, I want to note that there are a couple of specializations under which the 2 associahedra specialize to some families that we know and love. So the first one is when R is equal to 1, when there's only one circle. And in that case, we just have spheres with a single circle with one distinguished mark point. That's the same thing as disks with a bunch of boundary mark points, one of them distinguished. And therefore, in this case, we just get the associahedra. And the compactifications agree. And the way that's reflected in the algebra of simp is that what that's telling us is that if we just consider one Hom space, Hom from M0 to M1, we're getting an A infinity category, where that fact is coming from the fact that when R equals 1, the two associahedra are associahedra. And then the other specialization is that when we have two circles and one of them has no marked points on it, that's the same thing as disks with one interior circle tangent to the boundary at one point with boundary marked points. And as we said before, that's a realization of the multiplehedra. And that's corresponding to the fact that in simp, one of the operations on two morphisms is exactly Verheim-Woodward's functors associated to a Lagrange correspondence. Okay, great. So let's get back down to earth and do an example together. This is going to be 2M200 bar. So that's spheres with three circles, two mark points on the left circle. And just because it's easier to draw quickly, I'm going to think about those as disks like this with two interior circles with two mark points on the boundary. This is a trick that's possible to do exactly in the case that only the left circle has mark points. But in this case, that is the case. Okay, great. So we know the interior. What are some degenerations? One is when these two mark points come together, and then we just bubble off this unquilted disk right here. And then to get to this vertex here, we can do a further degeneration where the larger of the two interior circles here expands until it hits the boundary. And the convention is that when two circles, whether interior or boundary, collide, then you form a bubble wherever there's a mark point on one of those circles. So in this case, we think of this node here, this connecting point, as a mark point. And so when that larger of the two interior circles hits the boundary, we bubble off this quilted disk right here. So let me draw a couple more of these. To get to the bottom left edge, we'll glue in the outermost bubble to get that picture. Then a degeneration of that is when this circle here expands and hits the boundary, and there's two mark points on that boundary. And so we're going to get two bubbles. Sorry, just a moment. So then to get to the upper right edge, we could glue in the middle disk, that unquilted disk, to the main component. And so forth. And maybe I'll stop there so I don't run out of time. But I'll show you the kind of completed picture. There it is. And something that I want to come back to is this discussion we were having earlier with Emily and Jonathan, where in the case of associahedra, there's a canonical way to identify closed strata or closed faces with products of lower dimensional associahedra. And that actually exactly told us how to define the operatic structure. And so if we want to understand the operatic structure of two associahedra, we might try to do the same thing. As a first step, we might try to decompose the faces as products of lower dimensional two associahedra. And at first, that seems like it's working great. So for instance, if we look at this bottom edge down here, we can look at the two components separately. So this disk component here, and then this disk component. And so when you split those up, you get this guy.
It's a quick question in the chat. asking if all 2 associahedra are polytopes.
Yeah, good question. I put a lot of money on that. The underlying combinatorial object is an abstract polytope. The 2 associahedra themselves, the realizations, the ones I've been talking about, they're compact, metrizable spaces, they're homeomorphic to balls, they're stratified, and the poset of strata is an abstract polytope. It's Eulerian, so it's almost everything you can think of except for saying actually polytopes. A realization as a convex polytope is not so important for symplectic geometry, so I haven't thought about that part a lot, but I'm pretty sure that the answer is yes. And it might be an interesting question for someone who does, who studies convex polytopes.
Thank you very much.
You're welcome. Okay, so if we split apart this tree of quilted spheres like that, then what that's doing for us is it's telling us that this edge here decomposes as 2m sub 2 bar for that guy. There's just one circle and 2 marked points on it. And then 2m100 bar for this component. Great. But you start to run into trouble. And the place that you run into trouble for the first time is this upper right edge right here. So the way that you get to that edge from the interior is when both of the interior circles expand and hit the boundary. And when that happens, you'll bubble off 2 bubbles like this. And the tricky thing is that there's a constraint that we have to enforce between these 2 bubbles. And I'll get into that in detail on the next slide. But the spoiler is that you still do get a decomposition of this edge in terms of 2 associahedra, but this time it's not a product, it's a product of fiber products. And so what I mean by that is, as we'll see, there's a sort of forgetful map from 2 associahedra to associahedra. And we get 2m sub 2 bar for the main component times this fiber product of 2 copies of 2m100 bar, but with this fiber product condition. Okay, and that's sort of the first hint that whatever the 2 associahedra form, it's not just an operad, it's something a little bit more exotic. Okay, so why was that degeneration special? The point here is that if we look at an element of the interior, then we have these 2 widths, sort of strip widths, that I'm calling B and A here. And we can take this ratio of A over B, and it turns out that that's preserved by automorphisms. And so the point is that if we do this degeneration and we form these 2 bubbles here, each of those bubbles has the same modulus. I'm calling it A prime over B prime and A prime prime over B prime prime. But the fact that they were produced via the same limiting family of elements in the interior means that A prime over B prime equals A prime prime over B prime prime. And so that's why there's this constraint that we have to enforce among these 2 bubbles. Okay. Let's see. Just a moment. Right. So, so I'll come back to that in detail when I tell you what the operatic structure is. Before that, let me tell you a theorem which encapsulates these properties that I mentioned in response to Guillaume's question a minute ago. So in 2017, I showed that these things are stratified, compact, metrizable spaces whose posets of strata, which I call W sub n, is an abstract polytope. And here I'm writing down things that I've told you already, that there's a forgetful map from 2mn bar down to mr bar, where again, r is the length of n. And similarly on the level of the posets of strata. And the way that this works is very simple. On the interiors, if we take an element of 2mn bar, this guy here, and I'm using the plane presentation instead of the sphere one because it's easier here, we're going to forget the data of where all the blue points are and remember only where the lines are. And then we get a bunch of points on a copy of R, and that's exactly an element of the interior of MR bar. And then the next thing is that it turns out that the closed strata decompose as products of fiber products with respect to this forgetful map. And by the way, in the case that we were just talking about, the map down to M3 bar, with respect to which we're taking this fiber product, is exactly the map that sends one of these bubbles to the quantity A prime over B prime. Okay. And we can say something more about the structure of these spaces based on something I proved with Alexei Blomkov last year, which is that, moreover, they have a natural smooth structure as manifolds with generalized corners. And a consequence of that is that they're topological manifolds whose interior is the main stratum, which is homeomorphic to a ball, and therefore the whole space must be homeomorphic to a closed ball. Great. How generalized are the corners, Ezra asks? Yeah, I mean, pretty generalized. So what does that mean, generalized corners? It means that it's something like a manifold with corners, but you have too many faces meeting at vertices in particular. So for instance, in the case of three-dimensional two-associahedra, you could have 4 edges and 4 faces meeting at a vertex. Now, I don't think I can say any restriction on how generalized they can be. What I would say is this. So there's a complex version of two-associahedra, and the generalized corners in the complex setting translates into toric singularities, and those toric singularities can be pretty much arbitrarily bad as far as toric singularities go. Did that answer your question, Ezra? Great. Okay. And I wanted to show this picture again that was on the title slide. We've already seen this picture worked out. This is 2M200 bar. But I also wanted to show these two things on the right, which are two equivalent presentations of the poset of strata, W200 tree and W200 burr for bracketing. And so these are analogs for two associahedra of presentation of two presentations of the associahedra on the level of posets. So W200 tree is an analog of presenting associahedra as stable planted planar trees. And W200 burr is an analog of the presentation of associahedra as parenthesizations. So I don't have time to get into these presentations, but the point is that we have two combinatorial presentations that one can manipulate pretty well. Okay, great. So I can finally get to the operatic nature of the two associahedra. And to get into that, I want to recall how this works in my notation for the associahedra. So if we wanted to define the, this is just an example, the operatic composition that takes, and I should have written this as M3 bar times M2 bar to M4 bar. Then the way that this works is we take disks with 4 and 3 mark points, and we just stick the output of one of them to one of the inputs of the other. One example of that would be sticking this output here to this input. We get something like that. Okay. So the point is that we're including the product of this interval times a point into this pentagon as that upper left edge. And now we can do something like that with the two associahedra as long as we enforce suitable fiber product conditions. So down here, and let me zoom in a bit, we have a similar example to the last one we talked about, except instead of 2, 0, 0, we have 3, 0, 0. So that's a polyhedron, and I'm representing it by its net. So what I've done is you think about a polyhedron that you've cut open and flattened out. And then we're looking at this pentagon right here, and we're viewing that as the image of something akin to an operatic composition, where we're taking elements of 2m2 bar, this guy, times this fiber product here, and just sticking together these three quilted discs to get this guy here. And the point is that this only makes sense if we require that the moduli that I talked about earlier, the ratio of the yellow width to the red width among these two discs agrees. And so what we want to do is we want to formulate something like an operad, but where this sort of thing appears as a composition map. And so I'll tell you what we ended up calling that. And maybe something that I'll point out right now is that, you know, when I encountered this kind of thing, I thought it was probably an existing notion in operad theory. And I had a really hard time tracking down something that would allow for this sort of structure. And so Shakar Carmeli and I ended up writing down the notion of a relative to operad to do just that. And something that we found out after that is that one can interpret this in terms of Michael Batonen's theory of higher operads. And I'll come back to that in a minute. So what we're going to do is we're going to say that the two associahedra, they don't form an operad, but they form a quote unquote two operad relative to the operad of associahedra. And so to define this notion, we just took the properties that the two associahedra have and replaced the associahedra by an arbitrary operad called P down here, and then sort of use the properties of two associahedra to write down what we'd want a general relative to operad to satisfy. And so here's the definition. So we're working in the category with finite limits so that we can make sense of the notion of a fiber product. And what a relative to operad is it's a pair of an operad, P sub r, together with a bunch of things called Q sub m, indexed by the same kinds of things as the two associahedra, sequences of non-negative integers, which are not all zero. And what we require is that there are projections from Qm down to Pr, where r is the length of m, akin to the projection from a two associahedron to an associahedron. And then we require that there are compositions of this form where the P sub Si above this product means that it's a fiber product, satisfying the obvious coherences. And you know, I think I'm not going to take the trouble to unpack all of this because you know, it's just a bunch of notation that essentially says we want the sort of compositions that we saw already for the two associahedra. And so let me give you a quick example of a relative to operad that's not the two associahedra, called little squares in little strips. And I think that a comment of Paul Zeidel was the motivation for writing this down. So here we're going to take the operad P to be little intervals. So for instance, here's P3. It's the space of disjoint, 3 disjoint copies of an interval inside of a length 1 interval. And now what's Q sub n gonna be? Well, we're gonna take the square, the unit square, and we're gonna draw our vertical strips, and inside the ith vertical strip, we'll have n sub I squares. And so you can see an example of that here, Q20. So we have 2 strips, these green guys, and then 2 squares inside the first strip. And then down here, you can see an example of one of the compositions in this relative to operad. For some reason, when I wrote this down, I decided to choose a somewhat pathological composition, so sorry about that. But the point is that we start with an element of Q20, and what we want to do is slot similar pictures into the 2 blue squares or blue rectangles. And so here are those pictures. We're going to slot those in and get exactly this picture. And the point is that we need these 2 pictures to satisfy a fiber product condition. Oh, whoops, sorry. Okay, I keep hitting the button that unshares my screen. So we need these 2 guys to satisfy a fiber product condition that says that the 2 blue strips are the same strip, because if we didn't require that, we couldn't kind of slot this picture into here and this picture into here and extend the blue strips to make this picture coherent. So that's sort of a baby example of a relative to operad that, in particular demonstrates that the 2 associahedra are not the only example. And then there's a third example that's just an extension to a version of the 2 associahedra defined over C that Alexey Oblomkov and I wrote down last year. And one interesting thing about these is that they're not topologically trivial. In particular, as a special case, they include moduli of genus 0 stable curves. Okay. And then so the last thing I want to say in this section is that one can then define a category over a relative to operad, which finally allows us to define an A infinity 2 category, which was my goal in the first place, to define this thing called simp, this vehicle for functoriality of the Fukaya category, which was going to be something that was an A infinity 2 category. But initially, I didn't know what I meant by that. But finally, we can define that to be a category over the relative to operad of 2 associahedra. One question that I want to put out there that I wonder if higher category people might find interesting is that, so there's this standard fact that A infinity categories form a model for stable infinity 1 categories. And so what I wonder is there an analogous statement for A infinity 2 categories? Do they form a model for some sort of infinity 2 categories? And if they do, I would expect that it would be a rather simple, relatively finite model because of how concrete and finite the 2 associahedra themselves are. And finally, in this section, I want to make one remark about Michael Bottman's work, that he has this notion of n operads. And my understanding is that you can formulate relative to operads in terms of 2 operads and vice versa. That Bottman's notion of a 2 operad is exactly a relative to operad where the underlying operad is the associative operad. And vice versa, in a more complicated way, I believe you can interpret relative to operads as certain 2 operads. Okay, great. So I'll move on to the next section, but let me pause for a minute for any questions.
Can you back up one slide again? Just. I don't have a question. I just wanted to reread this.
Oh, sure. Okay, yeah. Yeah. And I will post these after the talk. So I have about 10 minutes left. So I'm going to say a bit about the connection between two issosahedra and the Fulton-McPherson operad. So there is this sort of provocative analogy that I think Jacob Lurie and Hiro Tanaka mentioned to me when I was talking to them a few years ago, which is that if you take an infinity 2 category and you consider such a thing with only one object, and you think only about the identity 1 morphism, and you ask what structure that is in terms of the 2 morphisms, then, so I've been told, that's the same thing as an algebra over E2. And so if there's some expected similarity between infinity 2 categories and a infinity 2 categories, you could ask what the connection is between 2 issosahedra and little 2 disks, which you actually would hope for from the symplectic point of view. It turns out to reflect a connection between the Fukaya category and something called symplectic cohomology. And so let me tell you a bit about why there is some connection. So there's this operad called the Fulton-McPherson operad, and I actually don't know who that's due to. I think it might be Ezra Getzler and JDS Jones, but I'm not sure. And so what this is you consider spheres with k+1 mark points, one of them distinguished, and you frame the output mark point. You quotient those by Mobius transformations and compactify that. Or an alternate presentation is we take R2 with a bunch of numbered mark points. We quotient by translations and dilations, but not rotations, and then compactify that. So that ends up giving you a 2k minus 3-dimensional manifold with corners. So for instance, in the case of FM2, we have 2 mark points in the plane. We can move the first mark point to the origin with translations. Then we can use dilations to move the second mark point a unit distance from the first. And therefore, you can see that we just get S1. And so the fact is that this gives us a model for the little 2 disks operad. A very nice model. It's an operad in finite dimensional manifolds with corners, and moreover, I'm not going to say it correctly, but the composition maps have a very nice form. And here's where the connection between little 2 disks and 2 issosahedra comes in. Say that we take any permutation, sigma, of k letters, and then we can write down this map, F sigma, which goes from a certain 2 issosahedron into Fm sub k. So it's the 2 issosahedron where you have 1 point on each of the circles, and there's k of those circles. And here's how the map is defined. At least on the interior. So we take R2 with a bunch of vertical lines. Whoops. And 1 mark point on each. And we're going to send that into Fm sub k by just forgetting all of the lines and numbering the mark points from left to right according to sigma. And that turns out to still make sense. That turns out to extend to the whole compactified configuration space. And so a conjecture that I made a little while back is that there should be cellular decompositions of FMK for all k, so that the operatic composition is cellular. And moreover, these maps between two associahedra and FM are also cellular. And I'm working on a preprint that should be out this fall that addresses this. And this is along the lines of some ideas that go back a ways. Specifically, originally in work of Getzler and Jones, there was this question put forward of how to decompose FM cellularly. And recently, last year, Paolo Salvatore wrote down such a decomposition using complex analysis, more or less. And an interesting thing is that Salvatore's approach is sort of completely different than what I'm working on. And I'll give you one relevant picture.
So in particular, you don't use complex analysis?
That's right.
Okay. I'd like to mention that Kontsevich and Sobelman were interested in this question, although they were thinking more in terms of chains than cells. Is there any relationship, do you think, between their ideas and your approach?
Something that I've been starting to try to understand is the relationship between two associahedra and cacti, which I think gets into what you're suggesting about the connection with Kontsevich and Soibelman's work. But I don't know yet. I hope to figure that out. So what I wrote down right here is a depiction of W111, or sorry, old habit, 2M111 bar. This is a polyhedron, and I've shown the net. So you cut it open and you flatten it out. The numbers here indicate which edges you'd have to glue together to get your polyhedron back. And so this maps into FM3. And FM3 turns out to be equal to S3 minus the neighborhood of a link with 3 components. And you can sort of very explicitly understand this map in this case. The shaded squares here indicate where the image of this thing run into the boundary of FM3, which is 3 disjoint tori. And in fact, in the specific case of arity3, it's very easy to write down a decomposition of FM3 that satisfies the properties I wrote down before, specifically that all of the maps from 2 associahedra are cellular. Okay, so I think I'm going to stop about there. And I just want to invite all of you operatic people that, you know, I'm really an outsider to operads. And if there are connections between what I've talked about today and things that you're familiar with, I would be very keen to hear about that. So I'll stop there. Thank you for your time.
Thanks for the nice talk.